Okay, so we've talked a lot about how to analyze data after you get it. So the next thing we're going to talk about in the class is if you have control over how the data are collected, what are some things you should think about when you're doing this? So this is the concept of experimental design. In many cases, you won't have control over the data collection. But in some cases you do. And when you do, you want to make smart decisions about how to collect the data. So let's start with some definition of terms that we're going to be using. I'll refer to experimental material. What I mean by this is like actual physical material that can be manipulated by the experimenter and measured, or can produce something else that can be measured. A treatment, which I'll often abbreviate as TMT. This is a condition that can be applied to the experimental material and controlled by the experimenter. A partition is just a division of the experimental material into groups, wherein each piece of experimental material belongs to exactly one group. So this may be somewhat of a new concept, but we'll give an example of this in just a minute. Now, an experimental design is just an assignment of the treatments to individual groups in the partition. So this is just how you decide to assign treatments in the experiment. Now there's a special kind of partition that's called the unit partition. This is the finest possible partition in which no two groups necessarily receive the same treatment. This is almost certainly going to be a new concept to you, so again, we're going to give some examples of this. The experimental units are just the groups in the unit partition, and the response, as we talked about before, this is just the measured outcome of interest. All right, let's jump into a couple of examples here. So we'll have two running examples throughout this lecture. The first one is going to be an agricultural example. So imagine that you have an agricultural field and you want to study the effect of changing the fertilizer that you use in the field. So you have an old fertilizer that you used last year, and you have a new one, and you want to do an experiment to figure out if the new one is better than the old one. Okay, so a partition so the experimental material is going to be the field. This is the thing that you're going to measure. This is the thing that you're going to apply treatments to, and it's going to produce something, a crop that you're going to measure the yield of. So a partition is a division of the experimental material into groups. So a partition in this example would be a division of the field into subfields. And so this is the picture on the right. So in each of these subfields, you might imagine applying a different fertilizer treatment to. So you might do old, new, so on and so forth. Now, if you've ever done agricultural experiments or worked in farming, this would be a really annoying experimental design. So if you did like old fertilizer, new, old. The reason is that typically fields are divided up into rows because to apply the fertilizer, you have to drive the tractor up a row of the field, and there'll be a spreader attached to the back of it that spreads the fertilizer as the tractor drives up the field. So for that reason, it would be much more convenient if you divided the field into a partition that looks like this, a partition of rows, and it also would be annoying if you had to stop in the middle of a row, switch the spreader to a different fertilizer, and then restart and move along the row. So for that reason, you might have a constraint on the experiment that you have to apply within a row. You have to apply the same fertilizer, But at the end of the row, you could switch to a different fertilizer and potentially apply a different fertilizer to the next row. So for that reason, the rows in this example are the unit partition, because you must apply the same fertilizer to all the locations within a row. But when you move to the next row, you have the option of switching to a different fertilizer. So therefore, the rows are the units. This division of the field into rows is the unit partition. All right, in the next example, we have an experiment involving rats. So the researcher wants to study how a hormone treatment influences the fertility of female rats. So again, in this case, the experiment is going to have a control. So in the experiment, they give the female rats an injection, and the injection either includes the hormone or a placebo. The idea in this experiment, you get, let's say, 20 female rats. You give each of them an injection that either contains the hormone or the placebo. Then you impregnate each rat. And then you measure the weights of all the rat pups. All right, so first question here, what are the experimental units? Are they the female rats or the rat pups? Let's think about this in terms of the definition of the experimental units. So let's go back up. So the unit partition is the finest possible partition in which no two groups necessarily receive the same treatment, and experimental units are the groups in the unit partition. So the experimental material is going to be these female rats, because we're going to apply the treatments to the female rats. And they're going to produce something that we measure. So the question is, are the units going to be the female rats or the rat pups? And the answer is that the rat pups can't possibly be the experimental units, because two rat pups from the same litter, meaning they had the same mother, necessarily receive the same treatment. So therefore, the units can't be the individual rat pups, because you can't decide to give one rat pup the hormone and another rat pup the placebo if they come from the same mother. So therefore, the units have to be the female rats, because each individual female rat can receive a different treatment. Okay. So aside from the treatments, there may be other variables that we expect to influence the response. So just for example, the weight of the female rat or attributes of the male rat that's used to impregnate the female rat. When we go to model the outcome, the responses, we can and should include these other variables in the model. And we should also consider these other variables when designing the experiment. All right, so that brings us to what is the goal of an experimental design. The goal is always to try to answer some kind of question. So the goal of an experimental design should be to design an experiment that gives ourselves the best chance of answering our question of interest. So if we have control over the design, we might as well pick a design that helps us, as long as it's not too costly or inconvenient. So we'll give, in the next lectures and in this lecture later on, we'll give some examples of experimental designs. And we'll give you some ideas for thinking about how to give good designs. But I think it's actually useful to talk about some examples of bad designs. And so you can think about what went wrong and how to avoid these types of mistakes. All right, let's start with bad design number 1 here at the bottom. So suppose we're doing the rat experiment and we have 20 female rats. First bad design would be to assign 18 female rats to the placebo group and 2 to the treatment group, the hormone group. This is obviously a bad design because we want to study this hormone, and this experiment doesn't give us much information about the weight of rat pups whose mother received the hormone treatment, because only 2 of them got it. All right, similarly, we could reverse the experiment and assign 18 female rats to the treatment group, the hormone group, and only 2 to the placebo group. This is also a bad design because even though this gives us a lot of information about the weight of rat pups whose mother received a hormone, it doesn't give us very much information about the placebo group, and therefore doesn't give us very much information about the difference between the placebo and the treatment group. Okay, let's do a couple more. Bad design 3 would be to randomly assign 10 female rats to the placebo group and 10 to the hormone group. So we're starting off good because we're putting 10 in each group. But then we impregnate the 10 placebo rats with a male rat number 1 and the 10 hormone rats with a different male rat number 2. Here, if we saw a difference between the placebo and the control group, we wouldn't be able to know whether the difference was due to the treatment, whether it got placebo or hormone, or whether there was something different about these 2 male rats that contributed to the difference in the rat pups. Okay, along a similar line, bad design number 4 would assign the 10 lightest female rats to the placebo and the 10 heavier rats to the hormone group. So you might get data that look like this, where the horizontal axis is the weight of the mother, and the vertical axis is the, say, average weight of the rat pups. So you might get data that looks like this. And here you wouldn't be able to tell is the reason that the hormone group is higher is that because the mothers of these rats got the hormone, or was it because the mother's weight was higher? All right, so these are bad design. What's a better design? A good design would be to get 10 male rats and group the female rats into pairs, where each pair of female rats has a similar weight. And then we randomly assign 1 female rat from each pair to the placebo and 1 to the hormone. And then impregnate both of these 2 rats with the same male rat and then use a different male rat on the next pair, so on and so forth. So this should seem kind of intuitive. We're controlling for the weight of the female rat by giving an equal allocation of the number of light rats and heavy rats to the 2 treatment groups, and we're making sure that the paired female rats get impregnated with the same male rat. Okay, so these ideas should seem pretty intuitive, and I think that generally researchers make good intuitive design decisions when they have full control over the experiment. Okay, so this good design here helps illustrate 2 of the key concepts in experimental design. The 2 concepts are blocking and randomization. The idea of blocking and randomization is that we want to control the experiment in some way so that we don't get an unequal allocation of treatments with respect to other variables that we expect to influence the response. So in these examples, the other variables that we expect to influence the response are the male rat and the weight of the female rat. So the idea with blocking is we make a non-random grouping of units according to known variables.
So in this good design here, we grouped the female rats according to their weight. So we in each group of female rats was a group of 2 rats. We made sure their weights were similar within each group. This allows us to ensure exactly or close to exact equal allocation of treatments to units with respect to this observed variable, which is the female rat weight. So that's for weight. We could also think of the male rats as blocks. So each male rat defines a block, and one of them gets treatment, one gets control. Now, we use blocking to control for variables that we can observe. But not all variables that we expect to influence the response can be observed. For example, we might not have enough resources in this experiment to genotype the female rats, and we expect the genetics of the female rat to influence the response, but that's not something that we can realistically observe in this experiment. So for variables that we can't observe, but we want to sort of protect ourselves against unequal allocation with respect to these unobserved variables, we use randomization. So randomization is a random allocation of treatments to units. And like I said here, this guards against a grossly unequal allocation of treatments to units with respect to unobserved variables. So thinking back to our blocks of 2 female rats, we don't know which of those 2, within each block, we don't know which of those 2 female rats would produce heavier offspring outside of the treatment that we're applying. So to guard against assigning the better female rat the treatment every time, we flip a coin and we assign the treatment randomly to those 2 female rats. That makes it very unlikely that in every group of 2 female rats we would assign the healthier female rat the hormone or the placebo, or vice versa. Okay, and the general rule of thumb with respect to blocking and randomization is you block over variables that you get to observe and randomize over everything else that you can't observe. So we can think of blocking as a constraint on randomization. And we'll talk in a later lecture more specifically about different types of blocked designs. So this is just a picture of that design we discussed above. So each square here represents a female rat, so there should be 20 squares. We group the female rats according to the 10 male rats. So the column headers here are a label. Well, there's only 8 here. So we had, say, in this experiment, we had 16 female rats. The 2 female rats below the label 1 are impregnated with male rat 1. And to assign the treatment or the control, we just flip a coin. If it comes up heads, we assign the first female rat to the treatment group. And we'll be looking at a lot of diagrams like this. So these kind of diagrams are useful for visualizing what the experimental design is. All right, so like I said, when researchers have control over the experiment, they often make good decisions. But I think problems tend to arise when some aspect of the experiment is outside of the researcher's control. So these are the things you have to really be careful about. So just to give an example, suppose you want to study 2 different hormones. The hormone B is on back order, but you're able to get hormone A. And so after you get hormone A, you go and get 10 female rats from the animal lab, and then do the experiment with hormone A while you wait for hormone B to arrive. When hormone B does arrive, you can finally finish the experiment, so you go back to the animal lab to get 10 more female rats. But once you get there, you learn that they've switched suppliers, and the 10 rats that they give you
are heavier than the 10 rats that they gave you the first time. So what do? I guess the only thing you really can do is try to convince yourself that the weight shouldn't matter. You could try to control for weight in the experiment, but then you would also have to worry about whether there's other aspects of these new rats from the new supplier that make them healthier or less healthy. Okay, so like I said before, the goal of an experimental design is to give yourself the best chance of answering your question of interest. Often the question can be formulated as, is there an effect of some variable? And often that can be translated to a hypothesis about a parameter in a statistical model. So the way we tend to formalize this idea of giving yourself the best chance of answering the question is by calculating something called the power. So the power of an experiment or an analysis is the probability of rejecting the null hypothesis. So in this example, the null hypothesis is that some parameter b1 is 0 when the true value of the parameter is something else that's hypothesized. So the power depends on the hypothesized value, an alternative hypothesized value of the parameter, and also it depends on what type of data you collect. So these power calculations can be somewhat arbitrary because you have to decide what's a reasonable alternative value of the parameter. So say you pick this to be 0.1. In that case, you would be asking what's the probability of detecting a true parameter value of not being equal to 0 when the true value is 0.1. And of course, this depends on the data you collect. This can be a complicated calculation, and potentially very complicated if it's a pretty complicated experiment. But it often, given some hypothesized value for the alternative hypothesized value for the parameter, often you can simplify maximizing the power, so you want to give yourself the best chance. You can simplify that to finding a design that minimizes the variance of your estimator of the parameter. So that's how we'll talk about comparing different designs. We want to give a design that gives a smaller variance of our estimator of the parameter, and that often corresponds to maximizing the power of the experiment. So again, power is really what you want to calculate, but often this is can be simplified to just finding a design that minimizes the variance of the parameter that you're trying to estimate. All right, so let's look at an example of design choice we can make where we can actually compute it's a pretty simple model where we can actually compute the variance of the parameter we're trying to estimate. All right, so in this example, we're going to stick with the rat example. We have 20 female rats, and we'll let little yij be the total weight of the ith litter from treatment group J. J equals 1 is placebo, J equals 2 is the hormone. And we model the data like this. Yij is B0 plus Bj epsilon ij. That means that rats from the placebo group have mean B0 plus B1. Rats from the hormone group have mean B0 plus B2. And therefore, the quantity that we're interested in is the difference between those two expected values, which is B2 minus B1. Now, we have 20 female rats, so our constraint is in the experiment is that we can assign treatments to these 20 rats. So if we assign 10 to the hormone group, we have to assign 10 to the placebo group. If we assign 12 to the hormone group, we only get 8 in the placebo group. So we can represent our design by a pair of numbers, n1 and n2, where n1 is the number in the placebo group and n2
is the number in the treatment group, but we have to pick N1 and N2 so that N1 plus N2 is equal to 20. All right, so it should come as no surprise that the least squares estimator of B2 minus B1 in this model is that you just take the average of the observations in the hormone group, so sum yi2 divided by n2, and subtract off the average of the observations in the placebo group. Because this has a simple form, we can just calculate what the variance of this estimator is. It ends up being this, sigma squared over n2 plus sigma squared over n1. This term comes from this part of the estimator. This term comes from this part. And so you can simplify this as sigma squared times 1 over n1 plus 1 over n2. And if you want to simplify it further, you could write it like this. This simplification comes from the fact that n1 plus n2 has to be equal to 20. All right, so the idea is we want to pick this design, n1 and n2, where n1 and n2 have to add up to 20, so that this variance is smaller. So the way we're going to do that is we're going to just pick a bunch of different values for n1 and n2 and calculate what this variance is. Now, if you want to minimize this, it doesn't matter what sigma squared is. You just have to minimize, no matter what sigma squared is, if you want to minimize sigma squared times 1 over n1 plus n1, n2. That just means you have to minimize 1 over n1 plus 1 over n2. So we're going to look at the value of this quantity for different choices of n1 and n2. All right, so that's what I've calculated in this table. I don't have all possible choices. You'd want the table to run from 1 up to 20. So I've just constrained this to the range 7 up to 13 for N1. So the top row is the number that you assign to the placebo group. The bottom row is the number that you assign to the hormone group. And of course, the top row plus the bottom row has to add up to 20. So 7 goes with 13, 8 goes with 12, and so on. And then below the line, I've calculated 1 over n1 plus 1 over n2. So the idea, again, is that you want to minimize this quantity. And if you just calculate it, you can see that it has its smallest value at n1 and n2 both equal to 10. All right, so this, again, should come as no surprise. The best experiment, if you're trying to estimate the difference between the hormone group and the treatment group, is to assign 10 to the hormone group and 10 to the treatment group. What might be slightly surprising is that if you do 9 and 11, you get something that's actually very, very close. So if for some reason you could only assign 9 to the, if you could only assign 9 to the hormone group, you actually don't lose a whole lot in terms of increasing the variance of the estimator.